The physical evidence begins with a single torn structural node. Deep in the cold storage of Lake Michigan rests a VOT F4U1 Birdcage Corsair BuNo number 02465. Painted with the training code F21, this airframe represents an extremely early production variant of a pivotal naval fighter. It went into the water on June 12, 1943. When an aircraft strikes water, investigators typically expect compression damage, crushed lower cowlings, and bent propeller blades. They do not expect a primary flight envelope safety mechanism to be violently extracted from its reinforced airframe mount. Yet the arresting hook assembly on this aircraft is entirely ripped out, leaving behind sheared metal that indicates a massive, isolated structural overload prior to the water impact. The wreckage lay undisturbed and unmapped for over 5 decades. Locating a specific, localized metal target within a massive body of freshwater requires systematic search geometries. The bottom of Lake Michigan features vast, flat stretches of soft sediment. Visual search is impossible due to the lack of ambient light penetration and suspended particulates. In 1995, a specialized recovery organization utilized side-scan sonar to run overlapping search transects across the designated grid. The sonar equipment emits acoustic pulses that reflect differently off hard surfaces compared to mud. When the acoustic waves struck the Corsair, the metal structure returned a high-intensity signal, casting a distinct acoustic shadow across the flat, acoustic return of the surrounding sediment. This signature confirmed the presence of an intact single-engine fighter resting on the lakebed. The coordinates were locked, establishing the physical site boundaries. The location was secured, but the vertical position imposed a hard operational boundary. The Corsair sits at a depth of 240 feet. This precise measurement places the wreck far below the reach of wind-driven wave action, winter ice scour, and standard recreational diving limits. Because the airframe remained undisturbed below this physical threshold, it entered an environmental state of suspended animation. The deep, freshwater environment is cold and comparatively stable, but it should not be described as an oxygen-free vault. In deep Lake Michigan, the large hypolimnion can retain enough dissolved oxygen through the season, while cold temperatures, darkness, and the absence of seawater salinity still slow many destructive processes. In marine environments, dissolved sodium chloride acts as a highly efficient electrolyte, accelerating galvanic corrosion between dissimilar metals and rapidly destroying aircraft aluminum. Freshwater also lacks the high chloride load and conductivity of seawater. Without that salt-driven electrolyte, galvanic attack and chloride pitting are reduced rather than eliminated. The cold, low-salinity water helped preserve the aluminum skin, the internal structural ribs, and even portions of the original wartime paint and primer layers. That preservation turned the wreck into a clean forensic baseline. The damage from June 12, 1943 could still be read against metal that had not been consumed by aggressive aquatic decay. Against that baseline, the torn hook mount becomes the central anomaly. A reinforced naval fighter hook mount is built to carry arresting wire loads into the fuselage spine, but water impact could not reproduce that same localized pull. The severed mount therefore points to an independent overload before the aircraft settled on the bottom. What precise kinetic threshold was crossed to shear a primary structural node completely out of the tail? A carrier approach operates on a rigid trade-off edge where the decision to land or abort must be executed before the aircraft crosses a critical spatial threshold. Committing to a late wave off requires the pilot to rapidly transition a descending aircraft into a climbing attitude by applying maximum throttle. This extreme power application creates an immediate hazard because the heavy airframe must overcome its downward momentum. During this specific transition phase, the aircraft physically settles lower toward the deck, before the engine thrust can generate enough lift to pull it upward. This settling effect dictates the precise boundary between a successful abort and a catastrophic deck strike. On the day of the accident, Ensign Carl Harold Johnson was conducting carrier qualification flights. His flight log recorded 388.5 total flight hours, yet he possessed only 57 hours of specific experience flying the F4U1 Corsair. This aircraft was an unforgiving machine for a novice pilot, demanding exact speed and attitude control. His designated target was the USS Wolverine. This vessel was not a fleet aircraft carrier, but rather a converted civilian paddle-wheel steamship operating on the enclosed waters of the lake to train naval aviators. The early configuration of this fighter featured a heavily framed birdcage canopy. This specific canopy design created significant blind spots. Because the aircraft required a nose-high attitude during the low-speed approach, the enormous engine, cowling, and heavy canopy framing completely obscured the forward field of view. To land safely, pilots relied entirely on continuous visual contact with the landing signal officer stationed at the stern of the ship. As the Corsair neared the deck, the USS Wolverine encountered a large wave trough. The vessel pitched down, dropping the wooden flight deck below the pilot's line of sight. With visual guidance gone, Johnson made the immediate procedural decision to abort. The aircraft settled just enough for the lowered arresting hook to strike the deck surface. The hook immediately caught the number 6 arresting wire. At this point, the operational mechanics completely inverted. The arresting gear is designed to catch a gliding aircraft with its throttle cut, using mechanical resistance to safely decelerate the mass. Instead, the number 6 wire grabbed a fighter operating under maximum forward acceleration. The opposing forces spiked instantly. Unable to contain the extreme tension, the number 6 wire snapped. The aircraft surged forward, but the hook remained engaged with the deck surface. A fraction of a second later, the hook violently snagged the number 7 wire. The second engagement drove a massive overload through a load path outside the mount's design limits. Catching the number 7 wire under full wave-off power radically exceeded the ultimate shear limit of the metal. The tail structure acted as a mechanical fuse. Instead of halting the accelerating fighter, the primary structural mount shattered, violently ripping the entire arresting hook assembly out of the airframe. Destabilized by the explosive structural failure and the sudden release of tension, the aircraft veered off the port side of the carrier. It plunged into the water. Upon striking the surface, the sudden deceleration and immense fluid drag concentrated extreme bending forces along the spine of the aircraft. The fuselage fractured completely, severing just a few feet behind the cockpit. The pilot survived the violent ditching and escaped the cockpit. The remains of the Corsair quickly sank. With the airframe resting on the bottom with a shattered spine, would the environment protect it permanently or present an entirely new biological threat? Then an entirely new biological variable altered the site conditions. Invasive quagga and zebra mussels fundamentally changed the underwater landscape of the region. These organisms require hard substrates to colonize, and an exposed metal airframe resting on soft sediment presents an ideal target. The mussels can attach to exposed metal and other hard surfaces, building a dense biological coating across the fuselage. That coating threatens the archaeological record by hiding surface detail, complicating documentation, and adding physical burden, but the exact number of shells and the precise structural load on this airframe have not been publicly documented. Furthermore, the biological layer can trap sediment, biofilm, and moisture against primer, paint, and bare metal, creating small local environments where corrosion may begin. Heavy incrustation made intervention more urgent, even though the exact load path and collapse threshold remain unverified in the public record. The window for intervention began closing rapidly as the structural integrity of the aircraft faced an accelerating threat of total collapse. Responding to this biological hazard required navigating a strict legal and administrative boundary. The United States Navy retains absolute legal ownership of all its sunken military craft, regardless of the passage of time or the specific location of the loss. The National Naval Aviation Museum, acting as the curatorial authority, recognized the immediate need to recover the airframe to prevent its destruction. However, the wreckage rested within the jurisdictional waters of a sovereign state. The Illinois State Historic Preservation Officer held a strict legal mandate to protect submerged cultural resources within those boundaries, ensuring that undocumented salvage operations did not destroy historically significant sites. Standard archaeological doctrine strongly dictates that historical wrecks should be preserved in situ. Leaving an artifact exactly where it rests maintains the contextual integrity of the site and prevents the immense risks associated with physical extraction. Based on this doctrine, the State Preservation Officer initially preferred that the site remain completely undisturbed. The friction centered on two opposing definitions of preservation. The state archaeological perspective viewed the intact debris field as a stable historical record that should not be violated by heavy industrial lifting equipment. The institutional perspective of the Naval Museum viewed the airframe as an actively degrading historical asset that would be completely destroyed if left on the bottom. To resolve the standoff, the museum and the Navy had to explicitly prove that the site was no longer in a state of suspended animation. They had to document that in situ, preservation had become the greater risk, not the safer default. Breaking the administrative stalemate required a formal memorandum of agreement. This document did not simply bypass the state preservation process. It converted the dispute into a controlled preservation undertaking. It recognized the Navy's ownership, the state's preservation concerns, and the adverse effect that removal could have on the broader Lake Michigan aircraft collection. The agreement required recording the aircraft before recovery, providing copies of that documentation, submitting a Navy-approved recovery and transport plan, and carrying out immediate stabilization and later conservation planning under the agreed conditions. With the agreement in place, the problem shifted from permission to engineering. How do you raise a severed airframe without tearing it apart? The extraction hinged on managing two crash-divided sections without asking the fracture to carry the load. Public accounts identify A and T recovery as the team working with the Navy and the National Naval Aviation Museum. The documented method was to place inflatable lift bags at strategic points, raise the wreckage to just below the surface, and keep the forward and rear sections separately supported during the long tow to the marina. Public sources do not verify detailed strap paths, water jet excavation, spreader bar geometry, or a heavy crane lift directly from depth. In November 2010, the recovery phase reached the surface stage. After the wreckage had been lifted with inflatable bags to just below the surface, it was towed for hours to a local marina, where the fighter finally emerged after 67 years underwater. The two damaged sections reached shore as a fragile but recoverable artifact. The original crash damage remained visible, and the aircraft could now move from underwater recovery into conservation triage. The Corsair cleared the water, and the next preservation threat began immediately. Uncontrolled drying and renewed corrosion chemistry, not a dramatic oxygen shock. Wet paint layers, trapped sediment, mineral deposits, and exposed metal can change rapidly when air, heat, and evaporation take over. If the airframe is allowed to dry in the open without conservation control, surviving paint can shrink or lift, contaminants can concentrate on the surface, and corrosion can resume in localized pockets. The first documented action was removal of the biological cover. Public accounts state that when the fighter emerged, mussels were scraped and hosed off the airframe before it was disassembled and transported to the National Naval Aviation Museum's restoration shop. The available sources do not confirm specialized wands, continuous rinsing schedules, or internal flushing details, so the sequence should remain at that documented level. Once the immediate cleaning and stabilization work was underway, the operation shifted to transport. The destination was the National Naval Aviation Museum in Pensacola, hundreds of miles away, and the wreckage had to travel without turning old crash damage into new handling damage. The approved recovery framework required planning for preservation during transport, but the public record does not verify the exact cradle materials, wrapping system, or moisture envelope used on the road. The defensible point is the transport consequence. The aircraft had to reach Pensacola without converting old crash damage into new handling damage. That successful transition delivered a fragile, wet, historically important artifact to conservation control. Halting the immediate decay secured the metal, but what would it take to permanently reverse the structural damage of the 1943 impact? 14 years of conservation and restoration defined the final operational phase for the recovered airframe. That immense time span was driven by the condition of the aircraft, the rarity of the early birdcage variant, and a curatorial preference for original material wherever it could be saved. A faster approach could have stripped away damaged metal and replaced more of the airframe with new fabrication. Instead, the restoration team prioritized preserving original skins where possible, retaining visible wartime markings, and rebuilding the aircraft around evidence rather than around a flawless display finish. This standard demanded a slow, deliberate workflow. Volunteers and technicians disassembled, cleaned, and restored the aircraft component by component, using Vought drawings when they existed and reverse engineering when they did not. The work preserved original skin forward of the radio compartment aft bulkhead, reused a substantial portion of the aft skins where damage allowed, and retained the visible F-21 identity on the fuselage sides. The public sources confirm the long restoration and component-level cleaning, but they do not verify a multi-year humidity reduction cycle for the complete airframe. With the surface material stabilized, the engineering focus turned to the airframe's damaged structure. The violent ditching and recovery history left the tail assembly among the most difficult areas to restore. According to the museum restoration account, the team used Vought drawings, reverse engineering, patch repairs, welding where needed, and internal rib work on the rudder and elevators to restore enough structural continuity for display while preserving the evidence-rich external shape and as much original skin as the condition allowed. The massive radial engine and its surrounding cowling components required their own preservation sequence. The public record supports careful component-level cleaning and restoration, but it does not specifically confirm chemical flushing of the cylinder banks. Reinstalling the preserved engine and cowling restored the aircraft's forward mass and profile without exceeding the documented record. The completed structural work returned the fighter to display geometry and allowed it to support its own static weight on its original landing gear struts. The canopy framing, characteristic of the early birdcage design, was carefully reassembled to enclose the preserved cockpit instrumentation. The completion of this extensive 14-year process secured an exceptionally rare technological artifact. Bureau number 02465 was the 312th Corsair airframe manufactured at Vought's Stratford, Connecticut facility, part of a production story that would eventually exceed 11,000 F4U and Goodyear FG versions, with broader Corsair family totals often counted above 12,000 across the full 11-year run. Due to the high attrition rate of early combat deployments and training accidents, early production variants were nearly wiped out of existence. Today, this specific airframe stands as one of only 4 surviving Birdcage Corsairs in the entire world. The strict adherence to evidence discipline, from the forensic reading of the torn arresting hook mount to the long, methodical restoration completed in 2024, preserved a primary source document of naval aviation. The aircraft now rests in permanent static display, a physical record of early carrier qualification limits and industrial engineering.